Okay, I want to start this deep dive with a mental exercise for you. I want you to hold two very different images in your head.
All right, I'm ready. Lay it on me.
They're separated by more than 30 years, but they're connected by the sheer terrifying indifference of the ocean.
Okay.
So the first image, it's pretty recent. This was back in 2021. You probably saw this on the news. It made the rounds. Two men from the Solomon Islands, Live Angicana and Junior Coloni.
Oh, yeah, I remember this story. Their little boat drifted off course.
Exactly. Their small boat gets lost, and they are out there just bobbing around in the Pacific Ocean for exactly 29 days.
29 days. I mean, that is a long, long time to be staring at nothing but water.
It's an eternity. And they survived on, I think it was oranges and coconuts they'd collected before they got lost.
Oh.
Here's the thing that really stuck with me, the kicker. When they were finally rescued off the coast of Papua New Guinea, Live gave this quote. He said, "I had no idea what was going on while I was out there. I didn't hear about COVID. It was a nice break from everything."
A nice break. That's darkly hilarious, isn't it?
Yeah.
To frame a near-death experience that way,
Very.
It really says something about how chaotic the world was in 2021, that being completely lost at sea felt like a vacation from it all.
It does, but now.
Yeah.
Now I want you to take that idea of a nice break and hold it up against the second image. This one is from July 1988.
Okay.
We're in the southern Indian Ocean. And it's the middle of winter. The water is freezing. The swells are the size of, apartment blocks. The wind is just howling at gale force. And there's another group of men, also adrift.
And let me guess.
Same amount of time?
Exactly 29 days.
Yeah.
But for the survivors of the MV Singa Sea, this was absolutely not a nice break. This was a descent into hell.
It's a really chilling parallel. And I think that's what we're really doing today, isn't it? We're conducting an autopsy.
An autopsy. That's a good way to put it. We're looking at the Singa Sea, not just as a survival story. And believe me, the survival part is incredible. But we're looking at it like a corpse. We need to dissect this massive 26,000-ton steel beast that didn't just sink. It snapped.
That's the mission. We have to look at the structural vulnerabilities of these ships, these bulk carriers. They call them the workhorses of the sea for a reason. And we need to understand the physics of why a 175-meter ship can just break in half like a dry twig.
And we absolutely have to talk about the bureaucratic failure, because the real tragedy of the Singa Sea isn't just that the ship sank. It's that the system, the whole safety net that was designed to save them.
AUSREP.
Yeah, the Australian Ship Reporting System. It completely failed to even notice they were gone.
That's the part that, honestly, it makes my blood boil when I read the report. The delay, the assumptions they made. We'll get into it. But we also have to talk about the legacy. Because if you work in logistics or maritime law, or, if you've ever just looked at a big ship and wondered, is that thing safe? You are living in a world that the Singa Sea disaster helped to create.
The ships of shame era. This disaster was one of the big catalysts. It forced a massive and long overdue cleanup of the entire industry.
So let's get into the weeds. We are not talking about some little fishing boat here. This is a massive industrial asset. So introduce us to the victim, the MV Singa Sea.
Okay, so she was a bulk carrier, built in Japan in 1976. Now, in the context of 1988, the year of the sinking, that makes her 12 years old.
Which, to someone not in the industry, that doesn't sound very old. I mean, my car is older than that. There are B-52 bombers still flying that are, 70 years old?
That's true. But the marine environment is, believe it or not, significantly more hostile than the upper atmosphere. Salt water is just relentless. In 1976, that vintage, it places her in a very specific era of shipbuilding.
Okay.
She was 175 meters long, so we're talking nearly 2 football fields, and she was registered in the Philippines.
Ah. And that brings up the whole flag of convenience issue right off the bat, doesn't it?
It does, and it's central to the story. But let's stick with her specs for a second. Her deadweight tonnage, or DWT, was 26,586 tons.
And just to clarify for everyone listening who might not be a maritime pro, DWT isn't the weight of the ship itself. That's displacement. DWT is basically the payload, right?
Spot on. It's everything you can put on the ship to make it sink lower in the water. So cargo, fuel, fresh water, ballast, provisions, the crew, all their stuff.
Yeah.
Everything. And on this final voyage, the Singa Sea was, she was working hard. She'd just left Bunbury in Western Australia, and she was fully loaded.
And the cargo is really the first antagonist in this story. I was looking at the loading manifest in the investigation report, and this was not a shipment of, fluffy cotton balls or electronics.
Oh, not at all.
Yeah.
She was carrying mineral sands, specifically ilmenite and zircon, and also copper ore.
Mineral sands, it's a deceptive name. You hear sand and you think of the beach. But this is heavy, heavy industrial stuff.
It's incredibly dense. And this brings us to a really important concept called the stowage factor. If you're loading something relatively light, like grain or coal, you physically fill up the cargo right to the hatch covers to hit your maximum weight limit. The ship is full in terms of volume.
Right, it's full.
But with something like copper, ore, or zircon, the material is so dense that you hit your maximum weight limit, that 26,000 tons, while the cargo holds are still, physically only about half full.
So you end up with these really dense, heavy piles of, dirt concentrated right at the bottom of the ship's holds.
Precisely. And this creates a very, very low center of gravity. Now, intuitively, that sounds like a good thing, right? Low center of gravity means the ship is stable. It won't capsize easily.
Yeah, that makes sense. But there's always a trade-off. It makes a ship stiff.
Stiff is the exact technical term. It means when the ship rolls in a ways, it snaps back upright incredibly violently. It doesn't have that gentle, slow, sort of comfortable roll of a cruise ship. It jerks. And that violent motion puts immense strain on the structure.
Wow.
But the bigger issue, the one that almost certainly killed the Singa Sea, is how that weight is distributed longitudinally. So from the front of the ship to the back.
This gets us to the stability book and the whole concept of hull stress. I saw in the notes from the report that Captain Douglas, who did the draft survey before they left port, he noted something pretty alarming about the ship's actual shape.
He did. He noted that the ship was hogged by 14.5 centimeters before they'd even finished loading all the cargo.
Okay, we have to unpack hogging and sagging. They sound like, terms from a pig farm, but in naval architecture, they are literally the difference between floating and breaking in two.
Right. It's simple physics.
Yeah.
So picture this ship as a long steel ruler or a beam. If you support that ruler only at the two ends, say you put it on two books, and then you put a heavyweight right in the middle.
The middle bows down?
The middle bows down. That is sagging. The deck is under compression. It's being squashed together, and the keel, the very bottom of the ship, is under tension. It's being pulled apart. Now, do the opposite. Put a support in the middle of the ruler and then push down on both ends. The ruler bows up in the middle. That is hogging.
So in that case, the deck is being pulled apart, it's under tension, and the bottom is being squashed together in compression.
Exactly. Now, ships are designed to be elastic. They're not meant to be perfectly rigid blocks. They have to flex with the waves. A certain amount of hog or sag is totally expected and allowable. But what Captain Douglas found was that the Singa Sea was hogged by 14.5 centimeters. That's almost half a foot, just sitting there in still water.
Which implies that the hull girder, the main structural spine of the ship, was already under a significant amount of pre-stress.
It was. And then it gets worse. After they finished loading and the ship was ready for sailing, it had reversed. She was then sagged by 9.5 centimeters. So in the span of just a few days, this massive steel beam went from being bent upwards to being bent downwards.
That is a huge amount of movement for steel. And speaking of the steel, the Singa Sea was built using high tensile steel. Now, usually when I hear high tensile, I think, upgrade, it's stronger.
It is stronger.
Yeah.
But in engineering, there is never, ever such a thing as a free lunch. Because the steel is stronger, the classification societies, the bodies that make the rules for shipbuilding, they allow the shipbuilders to use thinner plates.
To save weight, because a lighter ship means you can carry more cargo, which means more profit.
Precisely. So you have physically less metal present in the structure. A mild steel ship from an earlier era might have hull plates that are, say, 18 or 20 millimeters thick. A high-tensile ship like this one might use 14 or 15 millimeters.
And the problem is corrosion. Rust.
Rust doesn't care how strong your steel is. It eats away at a pretty constant rate. So if a 15-millimeter plate rusts by just 1 millimeter, you've lost a much more significant percentage of your structural strength compared to a thicker 20-millimeter plate.
And there's another issue with high-tensile steel, right? Fatigue.
It's much more prone to fatigue cracking. It's stiffer.
It's like the paperclip analogy. You can bend a paperclip back and forth a few times, but eventually that spot gets hot, it gets brittle, and then it just snaps.
And the Singa Sea had been bending back and forth, hogging and sagging in the ocean for 12 straight years.
Yeah.
So you have to paint the full picture. You've got a fatigue-prone hull, thinner plates because of the high-tensile steel, and almost certainly significant corrosion in the side shell frames because maintenance on these types of ships was often, well, let's be charitable and call it variable.
Variable is doing a lot of heavy lifting in that sentence. And this all touches on the genuine link problem in UNCLOS, the UN Convention on the Law of the Sea.
Right. UNCLOS requires a genuine link between a ship and its flag state. But in the late 80s, for many ships, that link was a complete fiction. You could have a Greek owner with a management company based in Hong Kong, the ship itself registered in the Philippines, carrying Australian cargo to a port in Rotterdam.
So who is actually responsible for checking if the rust in hold number 1 is getting to a critical point?
Everyone and no one. The Philippines Maritime Authority might not have the budget or the manpower to send inspectors all the way to Australia. The Australian port authorities, they'll check safety equipment like lifeboats, but maybe not the deep internal structure. And the Classification Society, well, they're paid by the ship owner.
Which is a textbook conflict of interest.
Exactly. So that is the state of the MV Singa Sea on July 2nd, 1988. She sails out of Bunbury, pointing her bow into the vast Indian Ocean. She has 25 crew members on board, mostly Filipino nationals.
And she is heading straight into the roaring 40s, in the middle of winter.
The southern Indian Ocean in July is a monster. The winds blow completely uninterrupted around the entire globe at that latitude. There is no landmass to slow them down between South America and Australia. The fetch, the distance the wind blows over the water, is effectively infinite.
And the weather report for July 4th, which is, Independence Day in the U.S., but it became a very, very dark day for this crew. It was just horrific. Gale force winds, swells hitting 6 to 7 meters, so 20, 25 feet.
And this is where the physics of the ocean meets the compromised physics of the ship. We have the testimony from the second officer, Sabas Martis. He is our primary witness to what happened at the end. He described being hit by 3 exceptionally large waves in very quick succession.
Now, people love to talk about rogue waves, these mythical 100-foot monsters, but the investigation points to something a bit more specific, and you could argue more dangerous for a ship like this: synchronous rolling and wave impact loading.
Yes, this isn't just about the height of the wave. It's about the period of the wave and the wavelength. So imagine the wavelength. The distance from one wave crest to the next is roughly the same length as the ship itself, about 175 meters.
Okay, I'm visualizing that. The ship fits perfectly between 2 crests.
So at one very specific, terrible moment, as the ship drives into the sea, the bow is riding up on one crest, and the stern is simultaneously riding up on the following crest.
So both ends of the ship are being held up by the water.
But the middle, the whole midsection of the ship, is hanging over the trough of the wave. There is no water supporting it. It is, for a split second, a bridge made of steel, suspended in thin air.
And that middle section is loaded down with thousands of tons of that super dense copper, or we talked about earlier.
Exactly. Gravity is pulling that middle section down with an incredible, incredible force. That is a moment of extreme sagging. The ship literally bends like a smile.
And then just as quickly, the wave moves on.
Seconds later, the situation is reversed. The middle of the ship rises onto a crest. Now the bow and the stern are hanging in the air over the troughs, completely unsupported. Gravity pulls both ends down. That is a moment of extreme hogging. The ship bends like a frown.
So she's being bent like a wire, up, down, violently.
And because the ship is stiff from that heavy cargo, this isn't some gentle flex, it's a violent snapping motion. Martis, the survivor, he said it happened in minutes. He heard a noise like a cannon shot.
And that was the sound of the deck plating failing.
That was the sound of the whole girder snapping in two. The main deck plating, this thick steel, literally tore apart. The ship didn't just take on water, she broke her back.
It is just terrifying to think about the scale of that violence. We think of steel as this permanent, strong thing, but here it failed catastrophically.
The survivors described a vortex. You have to imagine when 26,000 tons of ship and cargo suddenly head for the bottom of the ocean, they displace a massive amount of water. And that water has to rush back in. It creates a powerful suction.
I read Martis's account. He described being physically sucked down into the depths.
He thought he was dead. He said his lungs were burning. He was fighting against this whirlpool, and he was surrounded by this thick black oil slick because the ship's fuel tanks had ruptured instantly. He was swimming for his life in a toxic soup of freezing water and heavy fuel oil.
25 men go into the water. The ship is gone. And this is where we hit the second catastrophic failure, the silence. There was no SOS.
Nothing. Not a single peep.
But how is that possible? Even in 1988, they had radios. They had distress systems.
It just happened too fast. The radio room was on the bridge, in the superstructure at the back of the ship. When the ship snapped, and the evidence suggests it broke just forward of the bridge, the main power cables running from the engine room were severed instantly. The antennas on the Monkey Island, the roof of the bridge, probably came crashing down.
Didn't they have emergency batteries for the radio?
They did, but switching over to them takes time. Or the batteries themselves might have been damaged in the violence of the breakup. But the real issue, and this is a key part of the investigation and the legacy, was the lack of a float-free EPIRB.
EPRB, that's the emergency position indicating radio beacon.
Right. We see them on basically every commercial boat today.
Yeah, that little box in the canister.
Today, yes. Today, an EPIRB is mounted in what's called a hydrostatic release unit. If the ship sinks and that unit goes about 4 meters underwater, the water pressure automatically triggers a blade that cuts a strap. The beacon then floats to the surface, and it starts screaming a distress signal at a satellite.
But the Singa Sea didn't have that kind of setup.
No. In 1988, on this class of vessel, the EPIRB was likely stored in a bracket on the bridge, or maybe in one of the lifeboats. It was a manual device. You had to physically grab it, turn it on, and take it with you into the lifeboat.
And if you're being sucked down by a vortex in the middle of a gale force storm?
You are not thinking about grabbing the beacon. It sank with the ship.
Yeah.
So on July 4th, the Singa Sea completely vanishes from the face of the earth, and nobody knows.
And this brings us to the part of the story that, reading the report, made me the most angry, the failure of AUSRIP.
The Australian Ship Reporting System.
Right. Australia has search and rescue responsibility for this massive chunk of the Indian and Pacific Oceans. So they have this system where ships have to check in every 24 hours. Just a quick message. I'm here. I'm okay. Here's my course and speed.
It's the dead man switch principle.
Yeah.
If you don't call in, we have to assume something is wrong and come looking for you.
The Singa Sea sent its last report on July 3rd at noon. On July 4th, at 14:00 hours Western Standard Time, their next report was due. They missed it. The Federal Sea Safety Center, the FSSC in Canberra, they flagged it. Their system showed the report was missing. They knew. And yet, no plane was launched. No search was started.
Not for 72 hours.
3 days. I can't wrap my head around that. Why would you wait 3 days when a ship goes missing in a known major storm?
This is a classic, tragic case of what we now call incompetence bias, or maybe normalcy bias in these high reliability organizations. The investigation revealed a stunning lack of urgency. The supervisors at OTC Perth Radio, that's the coast station that handled the communications, they were talking with the safety center in Canberra. And the prevailing sentiment, the assumption they made was, oh, don't worry about it, the radio operator on that ship is just incompetent.
They blamed the victim before they even knew he was a victim.
Explicitly. The investigation records show they claimed the operator had inferior skills. They said he probably just didn't understand the reporting codes, or his equipment was faulty, or maybe he just forgot to send the report.
So they assumed radio silence meant broken radio, or bad employee, not sunken ship.
Precisely. They normalized the deviance. They had this mindset of, oh, these flag convenience ships, they're always missing their reports. It's probably nothing. And that fatal assumption cost them the golden day.
Explain the golden day. What does that mean in search and rescue?
In any SAR operation, the first 24 hours are everything. That's your golden window. The datum point, the last known location of the vessel, is fresh. The survivors, if there are any, are likely still close to where the incident happened. They're warmer, they're stronger, they're more alert.
But the ocean moves.
It moves fast. You've got the Llewellyn current, the West Australian current. Everything is swirling out there. Plus, you have wind drift acting on a lifeboat. The potential search area expands exponentially with every passing hour.
It's just geometry working against you.
Totally. If you start a search on day 1, you might be searching a box of, say, 50 square miles. By the time you get to day 3, you're searching a box of 5,000 square miles.
So by the time they finally launched a Royal Australian Air Force P-3 Orion on July 7th, the haystack had become the size of a small country.
And the weather conditions were still terrible. Which brings up another technical problem. Sea clutter.
Right. Radar isn't a magic wand that just sees everything.
No. Radar works by bouncing radio waves off objects. A big metal ship reflects that energy really well. But you know what else reflects radar energy? A massive wave. In a storm, the radar screen is just a mess of noise. That's the clutter. Trying to spot a tiny 5-meter fiberglass lifeboat in a sea of 5-meter white-capped waves using radar. It is next to impossible.
So the pilot is basically just relying on looking out the window at this chaotic, gray, churning ocean.
And seeing nothing. They flew their search grids. They saw absolutely nothing. And so they called off the search.
The file was closed. The official report, presumed lost with all hands.
And as far as the world was concerned, that was the end of the story. The bureaucracy checked the box that said resolved. But 6 men were still out there, in the cold.
So let's shift gears. Let's talk about Lifeboat 19, because this is where the cold, hard physics and the bureaucratic failure, this is where it gives way to the human element.
It really does. Out of 25 men thrown into that water, 7 of them initially make it to this single lifeboat. And we should be clear, this wasn't one of those enclosed orange capsules you see on modern ships that look like little submarines.
This is just an open boat.
An open fiberglass whaler, completely exposed to the wind, the rain, the freezing spray, everything.
You mentioned 7 men initially.
Yes. They managed to pull the chief officer from the water. But he had sustained severe head trauma during the violent breakup of the ship. He died shortly after they got him aboard the lifeboat.
Wow. That must have been just a devastating blow to morale right at the very beginning.
It sets an incredibly grim tone. They had to commit his body to the deep. So now there are 6 survivors. Salvas Martis, the second officer, who becomes the leader. Then there's the 4th engineer, an engineer cadet, a mess man, and 2 sailors.
And their supplies? What do they have to work with?
It was pitiful. A compass, a few flares, a tin of dry biscuits, and 20 liters of fresh water.
20 liters. That's the size of a standard office water cooler bottle for 6 men for an indefinite amount of time.
Let's just do the math on that. Basic human physiology says you need about 2 to 3 liters of water a day, minimum, just to keep your kidneys functioning and avoid delirium. They had 20 liters total. They had to make that last.
We mentioned Poon Lim in the show notes, the sailor who survived for 133 days alone in World War II. He's kind of the gold standard for this sort of thing, but he had a different set of problems.
He did. Poon Lim was adrift in the tropics, for the most part. His main problem was finding food and water. He had to learn to fish. He famously caught birds and drank their blood to survive because he ran out of fresh water. The Singa Sea survivors didn't have any fishing gear.
But they did have the storm.
The very same weather that sank their ship ended up saving their lives. The southern Indian Ocean in winter is wet. There were frequent storms. They used the boat's small sail, just a little piece of canvas to catch rainwater.
But just think about the discipline that requires. You are desperately dehydrated, your body is screaming for fluid, your lips are cracked, your tongue is swollen, and you manage to catch a liter of water. You have to trust the 5 other guys with you, not to just drink it all while you're asleep.
And that's where Salvas Martis comes in. Leadership in these extreme survival situations is fascinating. It's not about barking orders. It's about maintaining a shared reality, a shared belief that survival is actually possible. He set the ration. 1 dry biscuit per day. Half a glass of water per day.
And he took control of the flares.
This is the detail in the report that really gets me. They had a limited number of these handheld flares and parachute rockets. And every single time they saw a cloud on the horizon that looked a bit like a ship or a distant star that looked like a masthead light, the urge to fire a flare must have been absolutely overwhelming.
Just the urge to do something, anything.
Exactly. Panic tells you, fire the flare now. But reason in leadership says, wait. Martis refused to fire them. He hoarded them. He knew they only had a few shots, and he was not going to waste them on a maybe or a hallucination.
So they drifted for 29 days. We've sort of skipped over the physical toll. They were soaking wet constantly in subtropical winter conditions.
Hypothermia was a constant daily threat, but also saltwater sores. Their skin was essentially dissolving from being constantly abraded and soaked in salt water. They were sitting in a horrible mixture of salt water, urine, and the heavy fuel oil that had coated them when the ship first sank. By the 3rd week, they couldn't really stand up anymore. They were just skeletons wrapped in oil-soaked rags.
And unlike the 2 guys from the Solomon Islands who thought it was a nice break, these men knew for a fact that nobody was looking for them.
They were professional mariners. They knew how the search and rescue systems worked. They knew that after a week, maybe 10 days at most, the search is officially called off. They knew they were ghosts.
And yet, they kept the routine. 1 biscuit, half a glass of water, keep watch.
Until the night of August 2nd, or technically the early morning of August 3rd.
Describe that moment. What happened?
It's pitch black, middle of the ocean. Martis is on watch, and he sees lights. Real lights, not a star, not a hallucination from dehydration. Ship's lights.
It was the Standard Virtue, a Greek bulk carrier.
Yes. It was transiting the Indian Ocean, likely on a very similar Great Circle route to the one the Singa Sea had been on a month earlier. Martis gets the flare gun. He has the incredible discipline to wait. He waits until the ship is at its closest point of approach, what mariners call the CPA. And then he fires a single red parachute flare.
Just imagine being on the bridge of the Standard Virtue. It's the graveyard watch, midnight to 4 a.m. You are in the absolute middle of nowhere. thousands of miles from the nearest land. You're probably drinking coffee, trying to stay awake. And then suddenly, a single red star rises out of the water.
The officer on watch saw it. And to their immense credit, and this is a huge credit to that crew, they stopped. And stopping a fully loaded bulk carrier is not like hitting the brakes in your car. It takes miles to slow down and turn around. But they turned that massive ship around in the dark.
And they found them.
They found them. The report gives the coordinates: 34 degrees 19 minutes south, 112 degrees 22 minutes east.
How far had they drifted from where the ship went down?
Hundreds and hundreds of miles.
Yeah.
They were far to the south and east of the sinking position. They were nowhere near the original search grid from a month before. If the Australian Air Force had kept flying planes over the sinking site for 30 straight days, they never would have seen them. The ocean currents had taken them on a journey deep into the void.
I can't imagine the scene when they were pulled aboard the Standard Virtue.
The report says they couldn't walk. The crew of the Standard Virtue had to physically carry them up the gangway like children. They were emaciated, severely dehydrated, covered in these horrible boils and sores, but they were alive.
And they were able to confirm the fate of the other 19 men.
They told the captain of the rescue ship the whole story. The ship snapped in two. It sank in minutes. No other rafts were launched. It was just them.
That moment must be such a mix of pure, unadulterated relief, but also just pure devastating grief.
It is. But their survival, their testimony, it did something massive. It turned a maritime mystery into a global scandal.
Right. Because if they had died out there, the Singa Sea would have just been another statistic in the Lloyd's list of shipping losses. Vessel missing, cause unknown. End of story.
People would have speculated. They would have said maybe the cargo liquefied and shifted. Maybe they hit a submerged container. Maybe it was a rogue wave. But because Sabas Martis and his 5 crewmen lived, they could look the investigators in the eye and say, no, the ship broke.
And that direct, irrefutable eyewitness testimony is what lit the fuse for the Ships of Shame report.
1992. The Australian Parliament releases this report, Ships of Shame. And it was a bombshell. It sent shockwaves through the entire global shipping industry.
It wasn't just a dry technical report. It was an indictment of the dark side of the global economy.
It laid bare the economics of the shipping industry at the time. It showed, in black and white, that shippers were deliberately using old, rusty, poorly maintained flag of convenience vessels because they were cheap.
It's the classic race to the bottom.
Exactly. It also exposed the huge conflict of interest in the classification societies. Those are the private companies that are supposed to inspect ships and certify them as seaworthy. The report showed that if an inspector from one society was too strict, the ship owner would just threaten to move their entire fleet of ships to a different, more lenient society. So safety was actively being traded for market share.
So the story of the Singa Sea directly influenced SOLAS, the International Safety of Life at Sea Convention.
Hugely. Specifically, it led to the creation of SOLAS Chapter XII. This is the bulk carrier safety chapter. It mandated serious structural strengthening for these ships.
What kind of strengthening specifically?
They focused heavily on the transverse bulkheads, especially the bulkhead between hold number 1 and hold number 2, right at the front of the ship. The rule now says that the foremost hold must be strong enough to withstand complete flooding without causing the whole ship to fail.
Because the theory was that if the front hold floods, the bow dips down, the propeller comes out of the water at the back, and you lose all control.
Right. And the incredible extra weight of all that water in the front then snaps the hull, just like what happened to the Singa Sea. So they reinforced the ships. They also mandated water ingress alarms.
It sounds so basic. An alarm that just tells you, hey, there's water in the basement.
It does sound basic, but they didn't have them. The crew of the Singa Sea probably didn't know the hull was failing until the deck actually snapped beneath their feet. Now, sensors are mandatory in the cargo holds and ballast tanks. If water gets in, the bridge gets an alarm instantly. It buys you time.
Time to turn the ship to reduce the stress on the hull. Time to send an SOS. Time to get the crew to the lifeboats.
Exactly. And the EPIRBs. We have to come back to the beacons.
The Singa Sea was the death knell for the manual EPIRB.
It really was. After this, Australia pushed incredibly hard at the IMO, the International Maritime Organization, for mandatory float-free automatic EPIRBs on all commercial vessels.
And they changed the radio frequency they use, right?
Yes. That was a huge step. They moved away from the old 121.5 megahertz, which was an aviation frequency that required a plane to be flying relatively close by to even hear the beep. They moved to 406 megahertz.
Which talks to space.
It talks to the Cosmos satellite network, a global system.
Okay, so let's run the simulation. If the Singa Sea disaster happens today, in 2026, with a modern, compliant ship, what's different?
Well, ideally, the water ingress alarm in hold number 2 triggers first. The captain sees the alarm on the bridge. He knows the hull is breached. He sends an immediate digital distress call via the GMDSS, the Global Maritime Distress and Safety System.
But let's say it's just as catastrophic. It snaps instantly, just like it did in '88.
Okay, worst case scenario, catastrophic failure. The ship goes down in minutes. As it sinks, the hydrostatic release unit on the EPIRB canister hits 4 meters of depth. The pressure triggers it. It cuts the strap. The beacon floats free to the surface. It activates automatically.
And within minutes.
Within minutes, a satellite passing overhead picks up that 406 millihertz signal. It relays it to a ground station. The Rescue Coordination Center in Canberra gets a ping. And because all modern EPIRBs have a GPS receiver built in, they don't just know a ship is in trouble. They get a location accurate to within 100 meters.
So they aren't guessing. They aren't waiting for a missed report 24 hours later and then trying to calculate drift.
They know the ship is gone. They know exactly where the lifeboats are or where the debris field is. They are launching the jets and diverting other ships immediately.
The survivors of the Singa Sea waited 29 days. Today, they might wait 29 hours. Or, if they're lucky, even less.
That is the legacy. It's a cliche, but it's true. Safety regulations are written in blood. The sinking of the Singa Sea contributed 19 lives to that inkwell.
It's a heavy, heavy trade-off. But the data shows it worked. We lose far, far fewer bulk carriers today than we did in the 80s and 90s.
We do. But the danger is always complacency. We can't get complacent.
Before we wrap up, I want to touch on that C and Job source we looked at. It mentions how we're now trying to use technology to prevent the structural failure from happening in the first place.
Right. It's moving from reactive to proactive. Yeah. The BLU code, that's the bulk loading and unloading code, now mandates a detailed plan between the ship's officers and the shoreside terminal. The captain and the terminal operator have to sign off on a loading sequence. You can't just dump 5,000 tons of iron ore wherever you want as fast as you can.
And now we have digital twins. This is the real sci-fi stuff.
It is, but it's happening now. We can create a perfect digital model of the ship. We input the loading plan into the computer, and it simulates the exact hogging and sagging stresses on the hull girder before a single crane even moves. The computer can say, warning, if you load it this way, you will exceed stress limits and potentially snap the ship. So you change the plan.
And drones for inspections.
Drones are a huge game changer for inspection. Instead of building incredibly expensive and dangerous scaffolding to let a human surveyor climb up inside a dark, slippery, dangerous cargo hold to look for cracks, you just fly a drone in. It has high-def cameras, LiDAR, thermal imaging. It can spot a tiny fatigue crack that the human eye might miss.
So we have drones, satellites, AI models, digital twins. It really feels like we've tamed the risk.
And that is the most dangerous thought of all. That's the Titanic thought. We always think we tamed it. But you have to remember, the Singa Sea was considered a modern, well-equipped ship in 1988.
The sea is still the boss.
The sea is always the boss. All this technology is a safety net. But nets can tear, batteries die, sensors fail. And when that net tears, you're right back where we started. You are left with the human element.
You are left with Saba Smartus, holding that flare gun, counting out the biscuits, and just refusing to give up.
That's the ultimate takeaway for me. We can build better ships, we can write better laws, but we can't build a better ocean. And we can't engineer the human will to endure.
It's a humbling story. And if you really want to understand how the global supply chain was dragged, kicking and screaming into a safer era, and to see the human cost of that cleanup, I highly, highly recommend digging up the Ships of Shame report online. It's a grim read, but it's essential history.
It's a pivotal document in modern maritime history. Highly recommended.
Well, thanks for taking this dive with us. It was a heavy one, but a necessary one.
Always a pleasure.
Stay safe out there, check your EPIRBs, and we'll catch you on the next deep dive.